Hello, my name is Athan Reines, and today I'm here to talk to you about numeric computation. And the reason why I'm here is that I believe that Node and JavaScript are important new frontiers for doing numeric computing. And my hope is that by the end of this talk, the next time that you are faced with a task involving numeric computation, whenever you need to do number crunching, instead of reaching for R or Python or C or Fortran or Julia or Go or any other newfangled thing, you will leverage a budding ecosystem of libraries written in Node.js and with JavaScript for doing numeric computation. So the title of my talk is Peer-to-Peer Numeric Computing with JavaScript, which is probably a provocative title because admittedly the focus of this talk will be on numeric computing. Peer-to-peer is kind of like tacked on at the end just to show you what is possible with Node and with JavaScript that's hard to duplicate in other numeric computing environments. So the structure of this talk, first I'll go through about 4 to 5 different examples just to show you numeric compute applications written in JS. And then I'll discuss the why, and then I'll discuss the how, and then hopefully provide enough time, we'll get to the peer-to-peer demo, okay? So the first example is dbScan, which stands for Density-Based Spatial Clustering of Applications with Noise, which is a fancy way of saying birds of a feather flock together. Basically, the insight is that if you have a point, it should belong nearby to other points. And so you can basically define a local density, a threshold, and if there are a certain number of points proximate to another data point, you can say it's within that cluster. And then you can kind of iteratively go through and figure out, all right, where are my contour boundaries? So in this example, you can choose different data sets. I'll choose density bars. We initialize the algorithm, and then when we run it, we watch as the algorithm iteratively goes through and defines contour boundaries, defining what's a cluster and what's not a cluster. Okay? So it's another example. This time also doing 2D classification, but this time using neural networks. Neural networks are kind of the rage right now. Now the idea behind this interactive demo is that you can initialize some data, you can then add different points, and you can watch as the neural network achieves a different equilibrium, defining the contour boundaries within your data set. Another example using neural networks. So traditionally what you do with machine learning algorithms is that you give your algorithm a positive training data set. It looks for similarities within that data set. And then you give it a negative training data set, and it basically looks at the difference between what's in your positive and what's in your negative data set. And then hopefully the idea is that you can provide it some data that the model has never seen before, and it can correctly identify those features that you're hoping to select for. So in this case, neural networks have been trained for doing face detection for cats. So I can drag in images of cats, and I can watch as the algorithm iteratively goes through and identifies faces of cats. I can also, this is also the obligatory cat slide. I can also do it with multiple ones. There's a caveat to this algorithm. The cats need to have their eyes open and also facing the camera. And we can also do it with a negative data set, and we can see that the algorithm correctly identifies that there are no cats in this photo. So as the last kind of demonstration, there we go. And then full screen. Okay. This is 3-dimensional molecular modeling of biological molecules. On your left, you have porin, which is an integral membrane protein. And what this does is it allows for charged ion transport across the cellular membrane. On the right is MDM2, which is an oncoprotein. It's a protein related to cancer. And it is bound to another protein called P53, which is a genomic chaperone. Basically, it helps prevent your DNA from getting mutated. Now, these images are done in WebGL. And the more important takeaway behind these things is that in order to do this kind of rendering, to do like the salvation shell that you see over on the right, involves quite a bit of numerical computation. You need to do like matrix manipulation, you need to do vector manipulation, you need to like do various computations, right? So the common thread behind all these examples is that they're all written in JS, right? And they all allow for like tight coupling between doing visualization and your computation. And by having that tight feedback loop, you're able to develop insight into the algorithms and also identify like performance issues or how do they apply to different data sets. Now, typically when people think about numeric computing, they go, well, why would you ever use JavaScript, right? When you have like R, Python, or any of the other many libraries or frameworks out there for doing numeric computation. And there are many reasons to do things in JS. In fact, as a data scientist and as a full-stack engineer who's worked in Node quite a bit, I do all of my data science and analytics pretty much, more or less, using Node. And there are various reasons for that. The first being just sheer ubiquity. Basically, if you do things in Node and with JavaScript, you basically kind of solved your distribution, right? If I need to share my analysis or I need to share my computation and I want someone else to actually run that, they basically just need to open up a web page. And pretty much any device that can run a browser can run my analysis. The second issue is just performance. When you think about like just straight up like native primitives within a language, as a dynamic loosely typed language, JavaScript, when you compare it to other dynamic loosely typed languages like R and Python, is basically highly performant, right? You can basically get like a 2 to 3 times slowdown from native C code, which is crazy when you compare it to what you get in R and Python. The only thing that you can get with them right now is that you can get speed ups by writing your code in C and Fortran and having bindings, right? And so what you end up doing is you end up prototyping your code in R and Python, and then you do the real production level stuff in a true language, right? But what I've actually found when running or when doing numeric compute in JS and in production is the fact that oftentimes I don't need to actually dive down into a lower level language because JS is just fast enough, right? It's highly performant. Another reason for doing a lot of this is in-browser analysis. We've already seen with the demonstrations is the fact that you can have a tight coupling between interactive visualizations and your compute. What we've been seeing kind of like a trend within numeric computing is they have a kind of like split between your actual computation, your consumption. Well, if you can kind of bring those two together and have a tight feedback loop, it gives you better insight into your data analysis and also into the like actual runtime performance of your algorithms. And lastly, is that Node and in JavaScript lends itself very well to creating data pipelines, right? We already have kind of like abstractions that we all use in Node with streams, which makes it very easy to do incremental computation. When you work with like procedural languages like MATLAB or Mathematica or whatever to do computations, typically your data workflow is you do some kind of like bulk load, bulk transform, and then maybe you do some kind of like bulk output, right? Well, typically this isn't very resource efficient. You're often limited by the amount of data that you can load into memory, et cetera. But when you think about actually building out data pipelines, what can be much more efficient is doing incremental compute, where you do like, let's say, line-by-line analysis, and then do small little transformations over your entire data set. And of course, once you actually do this, you script it out with Node, you can easily build command line utilities, which kind of interoperate with all your other like shell data science utilities. So there are many, many libraries actually within Node that you can use to do numeric computing today, right? If you go to NPM and you do a search for like machine learning or clustering or time series analysis, you're bound to find modules out there that do things, right? There's actually a lot out there. This isn't like a new idea for doing numeric computing in JS, right? But one thing that's kind of that describes the ecosystem is the fact that, or one criticism of the Node ecosystem is that there's a lot of fragmentation, right? There's always like all these different libraries. How do you find out like what's good, what's bad, et cetera? Well, the reality is you just have to read the code. But there's a lot of good things out there. If you want to find an API that suits your taste, you can find one that does promises. If you like promises, you can do one find one that does promises. If you want like one that does callbacks, you can find one that does callbacks, right? Now, there's a lot of good things out there. The problem comes in when you actually want to bring all these together into a generic computing framework, right? Because they all have like differences like testing, documentation, API structure, code quality, et cetera. So what I'm going to talk to you about now is the fact that I've been working on a project now for a little over a year or so for doing numeric computing in JS, right? And I'll kind of walk you through what's in the project, what's available that you can use today. So the first thing that we've worked on is providing kind of like data structure primitives that allow you to do various transformations and data storage and data analytics, right? Everything from like enhancing an array primitives to building out two-dimensional structures like matrices to higher dimensional structures like ND arrays that you might find in Python and NumPy to building out data frames, something that's very common for doing data analysis in R and Python as well. So what do these look like? Well, they're just modules that you require and that you instantiate just like you might do an array. So here we're creating a matrix. You can define them in any different dimensions that you want. There's also like validation, so everything for doing like identifying positive zeros, safe integers, et cetera. The only reason these things are important is that when you actually build numeric computing utilities, especially within an interactive environment, it's very important that you do input argument validation, kind of like covering the loose ends of the fact that it's a loosely typed language. So you want to fail fast. And then kind of like building on top of these things, building like generic computation utilities. Everything from like special functions like error functions, gamma functions, beta functions, et cetera, to statistical analysis like quantiles, anything you might expect for like mean, standard deviation, variance, correlation, covariance, et cetera, to different matrix transformations, things like flipping a matrix from left to right, or rotating it, or skewing it, et cetera, to doing like distance metrics. If you guys are familiar with like document similarity, so like TF, IDF, you might be familiar with cosine similarity, or the Tversky index, or anything like this. Like all these utilities are kind of like built into this framework. And how these actually work? Well, they're just modules, once again, that you require. Everything's very modular, everything's separate, so you can kind of build and compose as you need to. But the primary like thing that unifies all these things is they provide like kind of like a standard interface, all talk the same language, all accept the different data structures. So in this case, we can instantiate a matrix, and then we can compute the mean across the different columns of that matrix. And of course, any of the compute functions will accept any of these different data structures and understand how to actually operate on them. There's also things for like doing statistical analysis, like statistical distributions whenever you want to model your data. Everything from like probability density functions to moment generating functions to generating random variates to performing statistical analysis, and many other things. So how these work? Well, once again, they're just modules that you require, right? So in this case, we can generate random normal variates and output it into a matrix. And of course, once they're in a matrix, every other compute function knows how to actually operate on those things. And then kind of continue on the theme of random data generation, we've also built various kind of like robust and seedable random number generators. Probably one of the deficiencies within JS is the fact that we have math.random, but the fact is you can't seed it, so you can't do like reproducible simulations, et cetera. So what we've done is we spent quite a bit of time implementing robust seedable random number generators, as well as just kind of like utilities to generate random data streams. So for example, if you wanted to generate random colors, or you want to do like random first names or whatever, you can do that. And then, as I mentioned, one of the things that Node is good for, which is data pipelining, also implement a lot of these things in streams. So many of you are familiar with how to use streams, but we've also kind of geared these to doing numeric compute. So everything from like splitting on new lines to doing various transformations. So if you guys are familiar with through or through to, map is your equivalent, joins, statistics, anything they can do numeric compute on. And how do these look? They're just individual modules that you require. So in this example, what we're doing is we're just reading from standard in, splitting on new lines, doing a transformation, kind of joining that back up into a new line delimited stream, and then piping that to standard out. And of course, once you do this in a scripting environment, you can also kind of bring this into your traditional command line utility pipeline. Also, we've built a whole bunch of a nice framework for doing charting. Of course, there are many different charting libraries out there, so I'm not really going to dwell too much on this. It's just we decided to roll our own so that they all can talk the same kind of language in terms of the data structures that they support. And then to help you kind of get started doing data analysis and kind of like just kind of get your feet wet, we've also provided a lot of canonical data sets, like the iris data set, to sentiment analysis lexicons, to like first name frequencies, so like census data and many other things. And once again, these are just all modules that you can individually require. So in this case, we import the iris data set, and then we have various transformation utilities to like transform it over into a matrix, or an ND array, or a data frame, right? So you can actually do your analysis. And then lastly, we basically combine all these things into an interactive notebook. So if any of you are familiar with IPython notebooks, or even more recently, the Tonic Dev notebook. So if you were yesterday at the QMiner talk, you saw them demonstrating how to use Tonic notebooks. Basically, we provide something very similar, but it comes basically preloaded with all these computation utilities. So you can do like reproducible analysis, you can share this and collaborate on it. It's very much a work in progress, pre-alpha, but much more to come on that in the upcoming year. So like, where are we now? How far along are we on the project? Well, there are over like 1,500 repos. More than 1,000 of those are currently public right now. There are over like 600 different published modules. So if you need to do some compute, the probability is that we've already like generated a utility for you to actually leverage and build that into your application. And there's a lot more to come on this regard. So the type of future work, just in terms of numeric computing that we're kind of working on, is basically kind of optimizing the workflow to help people if they want to build a new utility or kind of whatever integrate within the framework, basically providing a suite of utilities to get you up and going very quickly. Another thing is just kind of like rolling out more modules, kind of providing comprehensive documentation that kind of unifies all these different kind of organizations and what they do. And then finally, building a community around doing numeric computing within JS. So if you're interested in kind of providing feedback, or you have like feature requests or any kind of like issues, discussions, like each of those like little icons that were kind of previously logos, those are all different organizations on GitHub. If you go to the relevant organization on GitHub and you go to the discussions repo, just post your issues there, ask your questions, provide your feedback. Cool. So we still have about 5 minutes. That's good. So now what I'll talk to you a little bit about is peer-to-peer. So the primary goal here is that we want to be able to do RPC over a peer network, right? And this is something that's just not really possible. It's hard to duplicate in other numeric computing environments, right? Simply because they don't like operate in the browser. They're not necessarily like really web-enabled. Any kind of web technologies are kind of like tacked on. So just to kind of provide an overview of some of the different modules you can use, one is WebRTC, which is a native add-on that implements the WebRTC specification for peer connection and data channels. Another one is Simple Peer. If you guys are familiar with Feroz's work and WebTorrent.io, as well as Instant.io and ScreenCat, et cetera, they use Simple Peer under the hood. And then there's WebRTC Connect. If you guys were at David Diaz's talk on IPFS last night, he's the author of this. Multiplex. This is for doing multiplexing of binary streams. And then RPC multi-stream basically implements a JSON RPC protocol on top of multiplex. So these are the modules that we can use to do peer-to-peer numeric computing. So if you were to do RPC, traditionally how you would do it is you'd create an RPC server, you'd expose some methods, you'd create a client, you'd establish kind of a bidirectional communication channel between the two, and then once the methods are available to the client can start doing RPC and have the remote process execute those commands. So if you wanted to do this over a TCP socket, basically within that bidirectional communication channel, all you need to do is kind of like insert a TCP socket, right? And because Node.js, the net module, understands streams, this is quite straightforward to do. The only addition in comparison to the previous example is basically you just need to create a TCP server. Once that server is created and a client connects, and you establish that bidirectional communication stream, well, just like in the previous example, now you can start, the client can now start asking the server to run the RPC methods. So what's really nice about the WebRTC Connect module is it basically provides a very similar API that you might find in the net module. So you can like create a WebRTC server, and what that means is that you can essentially just kind of like swap out the net module for creating a TCP server and insert WRTC Connect. And now instead of doing RPC over a TCP socket, now you can do it over data channels, which means not only can you do server-to-server communication, but of course you can do browser-to-browser, browser-to-server, anything that can understand WebRTC. That's a pretty powerful concept, because you just can't do that in other numeric compute platforms. So this is the other peer. Once they connect, they can start exchanging information and start running the commands. So it's just kind of like a demonstration that this actually does work. Here what I'll do is I'll spin up one peer, which basically is just going to start listening, be ready for connections. And then I'll spin up a second peer, which is going to connect the client. And once they connect, basically they establish a communication channel. They go through various analysis phases. In this case, I'm just asking, both peers are asking the other peer to load up a data set and then load them into a matrix and then perform various numeric computations on them. So what we see is that Basically, they exchange some information, they signal to each other, we register some analysis phases, we write across the channel, and then finally we output all the analysis results, right? And what's nice about this is besides this being like server to server, you can do this browser to browser. I mean, things are not possible in other languages or frameworks. So if you're familiar with any of the code, obviously we kind of like breeze through kind of the demo and the peer-to-peer stuff. If you want to know anything more about it, just go to this URL. And spin up the talk. Basically everything within this talk is interactive. There's a whole lot of information that you can find out about like doing numeric compute, links to all the modules, et cetera. This work is not like solely my own. I have fantastic contributors. So Philip Burkhart, Robert Gisselson, and Rebecca Smith have been kind of instrumental in driving this project forward. And if you need to get in contact, here's my GitHub, NPM information, Twitter. Shoot me an email if you have any questions, or if you want to be added to the mailing list, I'll provide updates. And if you want to get involved, definitely get in contact. So that's it. I think there's time for like one question or two questions. You want the slide? Yep. Any questions? OK, that's it. Thanks for coming.